Okay, we are looking at problem 6, question 1. Okay, in this video. And in this particular question, what you've been asked to do is you've been asked to make a digital circuit. And what this digital circuit does is it takes two numbers, okay, A and B, but both A and B are 2-bit numbers. So you have 2 bits for A, which is A0 and A1. So this is a number A, and then you have a 2-bit number B, which is B0 and B1. Okay, and it compares these two values, and you have three outputs: greater, equal, or lesser. So if A is greater, then G becomes on. If A is equal to B, then E becomes on. If A is less than B, then L becomes on. Okay, and the first thing that you've been asked to do is you've been asked to do a truth table for the same. So if we write a truth table, you can just write the bits, isn't it? A0, A1, B0, B1. So these are your inputs, and your outputs are going to be G, E, and L. Okay, so that's your input output. And for A0, A1, B0, B1, you're going to have 16 combinations of inputs, right? So you can have 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0, and so on and so forth till 1 1 1 1. Okay, and now what we want to do is we want to see what the outputs are going to be. So take a look at the first input. So the number A is 0, right? 0 0, which means 0, and the number B is also 0, which means what is going to happen? Your greater than is going to be 0, your less than is going to be 0, and the equal is going to be 1. In the next number, B is 1 and A is 0. So basically A is less than B, right? So L is going to be 1. So L is going to be 1 and E and G are going to be 0. And the third number is the same. B is 2, and similarly for the fourth as well. It's going to be the same, right? Now in the fifth case, in this case, A is 1 and B is 0. So which means that A is greater than B. So we have 1 0 0, and then if you look at the next one, you have 1, A is 1 and B is also 1, right? Okay, wait a minute, I've been making a small mistake here. I've been saying that B is 1. Actually it's B1 that is 1. So what I'll do is, to make it I'll just make this B0 and then make this B1. A0, A1, and then what I was saying would be right. Yeah, so this is 1, A is 1, B is 1, and so they are both equal, which means that the output is going to be 1, and then G and L are going to be 0 in this case. And the last case that we'll look at, and you can fill up the rest of the table, is A is 1 and B is 2. So B is greater than A, or A is less than B. Okay, so L is 1 and G and E are 0, and you can fill this table up. Okay, so that's the first part A uh, of this problem. Okay, now let's take a look at how you're going to do part B. So in part B, what we have been asked to do is we have been asked to write the Boolean expressions that show the functioning of the digital circuit. So what you can do is you let's say we want to write the min terms. Remember what the min terms are? The min terms are the values are the are written for the outputs being equal to 1, right? So if you want to write the min term for G, so it's going to include this term. For E, it's going to include these two terms, Of course, there will be other terms both in G and E which come below in the table which you have not written. And for L, the minterm is going to be these values here, right? And for each of these minterms, we write a Boolean expression and then we OR those Boolean expressions, right? So what would be the minterm, let's say, corresponding to this uh, term here? The minterm corresponding to that is going to be, so you can look here, you can see that a1 is 0, a0 is 1, b1 is 0, and b0 is 0, right? So the minterm corresponding to that is going to be a1 bar, a0, b1 bar, b0, b0 bar, because b0 is also 0 at that point, right? And you write all the minterms. So G will be equal to this minterm plus the minterms corresponding to the other ones in the table. Okay, let's do L, and I think that will be a little bit more apparent. So let's start by writing the minterm for this one here. Okay, so what is it going to be? L will be equal to, the minterm for the one is going to be what? It's going to be A1 bar, A0 bar, B1 bar, B0, right? So it's going to be A1 bar, A0 bar, B1 bar, B0 plus it's the minterm for this second one here, and that's going to be what? A1 bar, A0 bar, B1, B0 bar. So if there's a 0, we put the bar, the not of A1, and if there's a 1, we just put the term as such. So what do we get? So we get A1 bar, A0 bar, B1, B, oops, B0 bar plus, then we have the minterm for this one, which is going to be simply A1 bar, A0 bar, B1, B0, right? And then lastly, we have the minterm for this one here, which is going to be A1 bar, A0, B1, B0 bar. So we have A1 bar, A0, B1, B0 bar. And then, of course, there will be other terms because we have not written all the terms in the truth table. Okay, hopefully that makes sense. Okay, so you can look at the complete solution on the solutions that I have provided to you. Okay, let's move on and let's take a look at the next part, which is 1C. So we are looking at 6.1C. Okay, and in this case, we have been asked to minimize these Boolean expressions. Okay, so if you draw a K-map of any one of these inputs, so let's say you are drawing the K-map for G, what you will get is something like this, right? This is a 4-input K-map, so you have 4 columns and 4 rows, and you can put, let's say, A1, A0 on this axis, on the horizontal axis, and B1, B0 on the vertical axis. And you can write the numbers 0, 0, 0, 1. Remember, you get 1, 1 first and then 1, 0. Similarly, 0, 0, 0, 1, 1, 1, and then 1, 0. And you can fill this table up from your truth table. And if you fill it up, I'll just put the solutions in. So what I got was something like this: 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, and 0, 0, 1, 0. And now what we want to do is we want to combine the ones into the biggest possible groups that we can, right? Of course, the groups have to be in powers of 2. So we could combine these 4 ones together isn't it? And then we are not able to come to include this one. I think the biggest group that we can get is these two. We can't get more than that. And to include this one, we can make a group with this one and this one being in a group. So there'll be three terms, right? One corresponding to uh, these four. So let's get that term. So what is the term corresponding to these four ones? So you can take a look here. B0 and B0 can take the values both 0 and 1. So B0 will not appear in the expression. Similarly, A0 takes the value 1 and 0 both. So that will not appear in the expression. So you'll have A1 and B1 in the expression. And A1 takes the value of 1, so you'll get A1 in the expression. And B1 takes the value of 0, so you'll have B1 bar. So your G, sorry about that. So G is going to be equal to A1 B1 bar plus, let's write the expression for these two ones. Okay, so that's the group that we want to make. So in this case, A1 takes the value of 0 and 1, so A1 will not appear in the expression. B1 and B0 are taking the value 0, A0 is taking the value 1. So what do we have? So what we have is B1 bar, because B1 is taking the value 0, B0 bar again because B0 takes the value of 0, and A0 takes the value of 1, so we have A0. Okay, and the last term is going to be the term corresponding to this group, this one and this one. Now let's take a look at these two. A1 and A0 take the values 1, 1, right? And B0 takes the value of 0, and B1 takes value 0 and 1. So B1 is eliminated because it's taking 0 and 1 both. And what we then get is A1, A0, and B0 bar. Okay, and that's our term for G. Similarly, what you can do is you can get the terms for L and E as well. You can look at the solution for the the complete solution. Okay, now let's try to implement this circuit using two input AND gates, and I'll do that in this same slide. So let's write the solution here. Okay, so that's part D. So what do we want to do? We want to do this AND operation, and we can do that using a two input AND gate, isn't it? So we have an AND gate here, and what we can do is we can just give it the inputs A1 and B1 bar. Of course, you can show that B1 bar is generated from a NOT gate, but I think this is enough. Okay, and then we want to generate this, but this is a 3-input AND operation, so we'll have to make that 3-input AND gate using two input AND gates, right? So you have something like this, so this goes in here, and then you have 3 inputs here. So you have B1 bar, B0 bar, and A0, and the output is going to be the AND of all these terms. And similarly, you can have another 3-input AND gate, and the inputs are going to be A1, A0, and B0 bar. Okay, and what we want to do is we want to OR these three terms, right? So let me just write what are we getting. So here what do we get? A1 B1 bar. Here what do we get? We get B1 bar, B0 bar, A0. And here what do we get? We get A1, A0, B0 bar, right? And we want to OR these terms. So how do we OR that? What we do is we OR these two terms first. So we do an OR like this, and then we use another 2-input OR to, oops, okay, I need to redraw that line, and we get this input here, and this is our output, the output of this OR gate. So that's how we generate G. Now in this question, you've been specifically asked to use 2 input gates, and that's why you need these many gates. But if you are not specifically told that, what you can do is you can just use a 3 input, you can use 3 input gates, right? So for example, if you wanted to generate this expression here, all you can do, if you didn't have to use 2 input gates, you can just have an AND gate with 3 inputs going in and 1 output. And similarly for an OR gate as well, you can do that. All right, so that is problem 1. Hopefully that is all right.